Yeah. I put homework out on termite. I tried to put it on Canvas, but maybe it didn't go. But it's on termite. Homework 9, and see that homework 8 is due tonight. 8 is due tonight. I'm going to talk a little bit about what I did last time. So, do you think this is Beiping weather? No. You know Beiping? You know, you know Beiping, huh? He knows. Beijing used to be called Beiping. Anyway, this is Beijing weather. We need a little snow. Okay, so last time we talked about the circuit with an input, with a stochastic input. This is a current source, and it's x of t. And this current source has a switch. Has a switch there, and it has a resistor in parallel with a capacitor. And the voltage at this point is y of t. It's a random variable. So we have a random input. So at t equal to 0, we open the switch. And then the current flows through the parallel RC circuit. And the voltage satisfies the portion of the current going through the capacitor is C dy dt. And the current going through the conductor is G times Y. And that's equal to the source current, X of t. Y is, or X is WSS, wide sense stationary, which means its autocorrelation function depends on the difference between Rx of T1, T2 is Rx of the difference, absolute value of the difference, minus T1 minus T2. Depends only on the difference. And that means Y is going to be WSS. So if X of t is wide sense stationary, that's a real function. So how would we solve the differential equation? Well, you do it in 2 steps, as we discussed last time. The transform omega, the transform of the random input is equal to the integral from 0 to infinity, right? Because it starts at t equals 0. And this would be x of t, e to the minus j omega t dt. Are we okay with that minus sign? Yeah, it's okay because x of t is 1 over 2 pi from minus infinity to plus infinity of x bar of omega. I put the bar over x. It's not a vector or anything. It's just the transform of the time variable. And this would be e to the plus j omega t times integral over omega. And same for y. Y of t is 1 over 2 pi. 0 to minus infinity plus infinity of y bar omega e to the j omega t d omega, and dy dt as a function of time is the derivative of y. It just means bring down j omega. Y bar of omega e to the j omega t d omega. So it's just got an extra j omega in there. So the differential equation means that c over 2 pi c over 2 pi j omega y bar of omega e to the j omega d omega. That's the first term of the differential equation. We take in the transform of the differential equation plus g over 2 pi. This would be y of omega t d omega. And that, of course, is equal to 1 over 2 pi x bar of omega e to the j omega t d omega. So I'm just repeating the differential equation. I just happen to take the Fourier transform of both sides, or at least the inverse Fourier, the Fourier transform. No, this is y of t, right? You've probably done this many times. So x bar of omega is equal j omega c y of omega plus g y of omega. So we have the solution y bar of omega is 1 over g plus j omega c times x times the input. So what we have is x bar of omega, input h of omega, and the output y bar of omega. Also, you could take the complex conjugate of this equation and have y of omega squared is equal to, this is h of omega, so we would call that h of omega quantity squared x of omega squared. So this would say the output power is equal to h of omega squared times the input power. The filter h of omega quantity squared looks something like this. So it's a low-pass filter, isn't it? Well, as we did last time, x of t1 is c, dy of t1 dt, the derivative with respect to t1, plus g times y of t1. And so we're free now to say x of t1 times x of t2 is equal c. This is the derivative with respect to t1 of y of t1 x of t2 plus gy of t1 at x of t2. By the way, if we're headed toward the calculation of the cross correlation x and y, but this is the autocorrelation of x. Now, if x of t happens to be a complex function, then autocorrelation complex x of t, the correlation function t1 and t2 of x is the expected value of xt1 times the complex conjugate of x at t2. That's if, well, it doesn't matter. It could be real, right? Because the complex conjugate of a real function is the function itself. So in some sense, this is a more generalized definition of the autocorrelation function. the random variable x. Nevertheless, if x of t is real, the autocorrelation function is symmetric about t1 and t2. In other words, if it's WSS, then this is Rx, absolute value of T1 minus T2. And so typically the difference is between the two times is called tau. So if you're on a scale here, T1 and this is T2, then the distance between the two is tau. And so we would write this Rx of absolute value of tau. That is, if you move T1 over here, then this thing would be negative. So that's why you use the magnitude of tau. Oh, that's kind of interesting, right? So what that means is Rx of tau is equal to Rx of minus tau. That is, the thing is symmetric. So if we pick, for example, on the axis T2, and this is T2, and this variable is T1, then the autocorrelation function is always symmetric about that. Nevertheless, we have the differential equation C T1 y of T1, this is x of T2, plus g y of T1, x of T2, and that's equal to x T1, x of T2. And now we're going to take the expected value of both sides. And this would be Rx, or you could call that Rxx. Let's assume, for example, T1 is greater than T2. Rx, this will be T1 minus T2. So in the picture, that we have, then we're saying T1 is in this range. If T1 is in this range, you'd have to change that to T2 minus T1. So we have solved the differential equation. Rxx of omega T2. And I'm taking the Fourier transform of both sides. but we're trying to solve the differential equation of the variable T1 because that's the way we wrote the differential equation. We're just assuming, for example, that T2 is fixed and solve the differential equation for T1. So we take the Fourier transform, and T1 is the variable. This is xy, excuse me. When I take the expected value, that would be c times the derivative with respect to T1 cross correlation xy T1 T2 plus g cross correlation xy T1 T2 equals 2 RXX. And the solution, 1 over G. H of omega RXX T1 T2. Oh, excuse me. I better put a bar over that. Oh, not yet, not yet, not yet, not yet. Bar over this. Bar over that. And so the question is, looks like we got RXX input to the filter, and we have coming out RXY coming out of the filter. Back to the differential equation. X of T1, Y of T2. Remember the first time we took X times XT1 times XT2. So now I'm multiplying by Y2, and so that's C dt1. This is a Y of T1, this is Y of T2. And plus G, Y of T1, Y of T2. Now we take the expected value of both sides. That's a thin E. So we have R, X, Y, T1, T2 equals C, D, T1, R, Y, Y, T1, T2. plus GRYY T1, T2. Same differential equation, which we already know how to find the solution. Stochastic input. You remember the telegraph signal. Telegraph signal. Signal input. What is the autocorrelation function of the telegraph signal? By the way, on page 379 of the textbook, there is the telegraph signal. We did the telegraph signal, spent a lot of time putting binomial processes together. That is, we did an experiment every second, only half second, and if we had a success, we counted the number of successes, right? On the telegraph signal, we said, we're going to change the polarity at every time we had a success. So instead of counting, we just reversed the polarity of the signal. The counting signal, N of t, was not wide sense stationary because the autocorrelation function did not depend on the difference in T1 and T2, or N and M, where we were talking about times T at 1 second, 2 second, 3 second, 4 second, and so on. But for Poisson, for the Poisson process, you can read page 379. The probability of K successes between T1 and T2 is equal to lambda let's call this period between T1 and T2, let's call that distance tau. And so the probability of K successes in that range between T1 and T2 depends only on the difference between T1 and T2, nothing else. The number of successes just depends on the difference between the two intervals. And so if we looked at the telegraph signal and say we chose this to be T1 and this to be T2, then we were only talking about the number of successes in that interval. 1, 2, 3, 4 successes. So there's an even number of successes in that interval tau. It keeps the same polarity. If it changes polarity, 1, 2, 3, there would be an odd number of successes. So what we write is the probability that x at T2 equals 1 and x at, let's put T1 and T2 like that. I'm gonna make this T2 and we're gonna put that as T1. So the probability that x at T1 equals 1 and x at T2 equals 1 is the probability x of T1 equals 1 given x at T2 equals 1 times the probability of x at T2 equals 1. And so you can go down that list. In other words, you've got 1 x at T1, x at T2. You've got 1, 1, 0, 1, 1, minus 1, 1, 1, minus 1, minus 1. And at T2, you can get 1, minus 1, 1, 1, minus 1. When we calculate the autocorrelation, we have to take all 4 cases. And so we would need, in this case here, the probability that x at T1 equals 1 given x at T2 equals 1 times the probability that x at T times the probability of x at T1. Well, the probability that x at T1 is equal to 1 is a half. The telegraph signal doesn't prefer positive polarity over negative polarity. There's as many positive pulses as negative ones, regardless of what p is or the average value lambda. And so this would be the probability x of T1 equals 1 given x of T2 equals minus 1. And this is the times 1/2 probability x at t1 equals minus 1 given x at t2 equals 1 times 1/2. And the probability that x at t1 equals minus 1 given x at t2 equals minus 1 times 1/2. 1/2, 1/2. These two talk about an odd number of transitions, right? Changes polarity. 1 to minus 1, minus 1 to 1. They're both odd polarity, odd number of successes between. So those two are for the odd number of successes. These two are even, odd and even. So we got two of these. But you also have 1/2, right? So if you add up these two, it'd be negative, right? Right. Or x at t1, t2 is one, this one plus this one plus this one, probability of even number of successes times the probability of even number of successes. Minus 1 times the probability of odd number of successes. Okay, we'll call this P even and this P odd. P even and P odd. So what is P even equal to? Probability. Well, that's we call that period tau. So that's lambda times tau raised to the 0. Zero's even, isn't it? Over 0 factorial e to the minus lambda tau. Plus, what's the next even? 2 lambda tau squared 2 factorial e to the minus lambda tau. Okay, this keeps going, but that's equal to the summation lambda tau raised to the power k over k factorial e to the minus lambda tau, k equals 0, 1, 2, infinity. Actually, you could put k equals to 2L. L is equal 1 to infinity. The odd cases the odd cases, the only thing would be that k would equal 1, 3, 5, etc. So let lambda tau equal to alpha. So every one of these has e to the minus lambda tau, right? So this doesn't depend on the sum. So that's equal, alpha. And so p of even e to the minus alpha summation k equals 0 to infinity alpha to the k over k factorial, and that's equal e to the minus alpha times the hyperbolic cosine of alpha. That sum just happens to be. And the odd is e to the minus alpha hyperbolic sine of alpha. And so we have r x tau equals e to the minus alpha times cos alpha minus sine alpha. Remember, the minus sign is because the telegraph signal goes negative, goes from positive to negative. If the telegraph signal goes from positive to 0, this term wouldn't be there. Would not be there. But in any event, the answer is e to the minus 2 lambda t1 minus t2 if t1 greater than t2, it's e to the minus 2 lambda t2 minus t1 if t1 is less than t2. Symmetric about then t2. So this is t2, and so the autocorrelation function looks like that. And this is the t1 axis. If t2 moves back to 0, goes back there. This thing is always symmetric about t2. Or if you prefer to the variable tau, then it's e to the minus 2 lambda times tau, absolute value. Symmetric. By the way, this thing, if lambda gets big, what does that mean? This thing squeezes in, doesn't it? Squeezes in. So we want to calculate for telegraph input. R bar X of omega T2 is equal to the integral from 0 to T2 e to the minus 2 lambda T2 minus T1 e to the j e to the minus j omega T1 dt1. Okay. So here is T2. And so this integral represents that integral. What about over here? Plus. Oh, that's T2. Right. We're in the axis is T1. So we integrate 0 to T2 on T1. And so that's that function. So now we can integrate from T2 to infinity. And this function changes. Minus 2 lambda T1 minus T2 e to the j omega T1 dt1. So this thing integrates too. I got here a whole page of algebra. That was the first integral. And this is the second integral. Let's see. Yep, that's it. Now, look at this part here. If 2 lambda T2 is much, much greater than 1, we can drop that. What this approximation means is that T2 is big enough so that this thing dies off. Right before it reaches the origin, dies off. And so what we have Rxx omega T2 is approximately 4 lambda divided by omega squared plus 4 lambda squared e to the minus j omega T2. So now what do we do? Rxy now, omega T2 is 4 lambda divided by 2. This is a lot of algebra between here. Integral from minus infinity to this is T1, T2. And this integral is 1 e to the j omega T1 minus T2. And so 1 plus j omega RC time constant times omega squared plus 4 lambda squared d omega. Oh, that is a mess. Okay, after about 4 pages of calculation, T1, T2 happens to be 4 lambda over C. 1 over 4 lambda squared minus Tc squared e to the minus tau over Tc minus 2 lambda tau. That's what it looks like. What a mess, isn't it? You know, essentially, you have R, X, X, input to H of omega, that outputs XY. XY is the input to H of omega, and that outputs RYY. You know, the concept is sort of simple, right? But the devil is in the details. The devil, details. Details. How much details can you do on the final? If I gave this problem to you on the final, would you need some cheat sheet? Would you like a cheat sheet for the final? You want me to make it out? Huh? Uh, on the last day of class, I want you to bring your cheat sheets and we'll have a conference to see what goes on the cheat sheet. Okay? And everybody will have the same cheat sheet. Is that okay with you? Okay. Time averages. Time averages. Ensemble. Time averages. X of t. We take the time average of a signal, x of t. It's just simply 1 over 2t. The integral from minus t to plus t, x of t dt. That's all time average is. Ensemble average. What would you call ensemble average? Expected value? Well, an ensemble average, mu x is 1 over n. X of t, zeta I is 1 to n. Remember, 2. What's the average? 2. 6. Now, what's the average? Huh? It's 5, isn't it? What's the average? You know what, if I throw this die long enough, what the average would be? Well, if I throw a 5 one time and a 11 the next time, what's the average? A 5 and 11, it's 8. But suppose I throw a 1 and a 1, what's the average? Okay, suppose I throw a 1 and a 4, what's the average? Two and a half. So if I throw this die long enough, the average is going to be 3.5. I think. That doesn't mean it'll be 3.5. That just means in probability it'll be 3.5. The mean in probability. Chebyshev had his theorem on upper bounds and so on, but you can use Chebyshev to make an argument. This business here could be expected value of the random variable t and zeta. Those two might mean the same thing. But This is a time average here, and this is an ensemble average. But it depends on the specific experiment. I mean, if I throw the die 100 times, I'm not going to come up with the same average. But if I throw it 1,000 times, I probably come up with an average several 1,000 times one day. Next day I throw it 1,000 times. The average will be different. When is time average the same as ensemble average? Would somebody like to guess at that? I got $5. See that? See that picture there, right there? That was me. Okay. Reminds me of me. Firefox, you know, Google, when I'm on my computer, Google knows more about me than I know about me. Particularly if you buy stuff off of the internet, Google knows where you bought it from. And then they'll put advertisements. Look, see that even Firefox wants to sign in. Where is the oh, that's not. Okay, so here is, where's our voice? Is it over here? Do we know where the voice is? Beyond Lee, Beyond Lee, Beyond Lee. Bianli, Bianli. Is that the way you say it? What's that mean? Does that mean anything? What? We don't have sound. Okay, so it's Beyond Lee, Beyond Lee, Beyond Lee. Do we know what that means? No? It's just a word, isn't it? X of t is WSS, ergodic. White stationary, then the power spectral density of S of Rx of tau J omega tau d tau. The Fourier transform, as Willie Sutton is famous for, the power spectral density is the Fourier transform of the autocorrelation That's Einstein, Wiener, Kenshin. Kenshin, Chin. And Mao. You know, in Tiananmen Square, they're going to take Mao's picture down. And they're going to put Xi's picture up. Or maybe Jiang Jie-su. Einstein-Wiener-Kenshin theorem. It says the power spectral density is the Fourier transform of the autocorrelation function. Look at this. Here's x of f transform. Going into h of f, or h of omega, let's make it omega. And out comes y of omega. The power spectral density, x bar squared of omega, is equal h of omega squared times y of omega squared. I guess I put the square outside. This is the input power spectral density. And this is the output. What is the power spectral density of the telegraph signal? We know. Power spectral density of the telegraph signal, S, Sx, power spectral density of omega is equal to Fourier transform e to the minus 2, I'll keep that lambda, tau, e to the j, omega tau, d tau. That's the power spectral density of the autocorrelation function. This is the power spectral density of x of omega. What is that? It's just the Fourier transform of the autocorrelation function. So x of omega squared equals that. I'm going to show you a trick here on this integration. This is the integral 2 times the integral from 0 to infinity, e to the minus 2 lambda tau times the cosine of omega tau d tau. Why did I write 2 and integrate 0 to infinity? Because j omega tau is the cosine of omega tau plus j sine omega tau. But the sine of omega tau, which is odd, times an even function integrated over equal limits, negative and positive, yields 0. And the cosine is even, that's even, so it's just 2 times. Okay? Now, this is 2 times the real part of the integral, e to the minus 2 lambda tau, e to the j omega tau d tau. Right? Because the real part of e to the j omega tau is the cosine. Now we have 2 exponentials we can integrate. We're going to make the problem that I spent 2 days grinding through, we're going to solve it in about 15 minutes. Okay, the homework's on termite. Homework 9, due Monday night. Okay.